Hi, and welcome back to the Low Level Devil Channel's Raspberry Pi Bare Metal series. In the previous video, we implemented the process of booting our kernel into exception level 1. Now I want to get started with handling system interrupts. So let's get started. First, we will create a header file, entry.h, which will have some of our defines related to the different exception types that can be configured in the interrupt controller. So we'll start with our pragma once. So this is going to be in section D1.10.2 of the ARM reference manual here. Now when an interrupt occurs, execution is forced into an address that is the exception vector for the exception. The exception vector is in a vector table that is specified at the specific exception level that the code was running in. And each of these exception levels has a virtual base address register, which defines the base address for the table at the exception level and has each of these four possible types: synchronous exception, S-error, IRQ, and FIQ. And there's one for each of the exception levels. So I'm just going to paste in some of these defines here. This is for EL1T. We have sync, IRQ, FIQ, and error. So we also are going to have this for EL1H as well. You'll see here is EL1T and here is EL1H. So we'll have actually four sets total. We have those two, and then we have one for EL0 in 64-bit and one for EL0 in 32-bit. So in all, there's 16 specific different types where we can handle our exceptions. Now let's go and create a new file here. We'll call it entry.s, and this is going to be the assembly code. First we're going to include our entry header. So now we're going to set up this vector table, and what I'm going to do is just paste this in here. First we have to have an align here, and we have our global vectors variable, our position that we're setting up here. So you can see we have each of those four values here, and then the four different sets for EL1T, EL1H, EL064, and EL032. And we're using this ventry macro here, which is actually one we're just going to create. It's a really simple macro, so all that it's really going to do is take in a label and jump to that label. So we're doing a branch to that label. We're using a line 7 because it's a requirement on the size of each of these exception vectors. So now we're branching to these labels, but where are these labels exactly? Well, I'm just going to paste them down here. We have one label after each ventry, so we just want to paste these locations down here so we can jump to them when we receive one of these interrupts. You'll see we got ventry sync error here goes to here, which calls this handle invalid entry, passing the sync invalid EL1T, which is straight from our entry header file here. So that's where we're actually using these defines. Then we have one for the next one, and so on, FIQ and error. So and this is the one that we're going to actually care about here, the handle EL1 IRQ, because in that one we're actually going to have a handler for it, which, okay, I don't have that here yet, it looks like. We'll worry about that one later. So basically what I want to show you here is we have this handle invalid entry method here, or assembly function. It's a macro actually. So we pass in type, and that calls another macro called kernel entry, which we'll get to a little bit later. But essentially what it does is it's going to pass three parameters. First the type into x0, then the ESR EL1 into x1, and the ELR EL1 into x2. And then it's going to branch to this function, show invalid entry error message, which we'll write in the C code. And then it's going to jump to this error hang, because if it received an unknown error, we can't really do anything but just hang it. So we'll just paste this little error handler down here, which is essentially going to loop forever. So now here is our handle EL1 IRQ, which when we get an actual IRQ that we want to handle, we're going to jump down to here. And this is essentially going to call the kernel entry handle, call our handle method in C, and then kernel exit. So now let's get into the details of what this kernel entry is going to look like. Now, essentially, what we want to do is when we get an exception, we're jumping outside of our regular context. So we want to store the state of the processor before we do anything. And one thing that we're going to have to use is our stack frame size, which is 256 right here. So the very first thing that we want to do, let's end M here. Yeah, the very first thing we want to do is subtract from the stack pointer the value S frame size. So we're doing this to make room for the variables we want to store on the stack. So we're going to use the STP. We'll use x0 and x1, the stack pointer, offset by 16 times 0, which of course is 0. So we jump back the frame size and now we start storing. So we'll do the same thing for x2 and x3, and now we're going to go by the stack frame with the offset of 16 times 1. So we're essentially going to do the same thing for all of our registers, store all of our registers 4, 5, 6, 7, 8, 9, and so on up to 30. And again, we're every time we do, we're incrementing by 16, which those all add up to this stack frame size with a little bit of room to spare. So basically, you're jumping back, storing our variables, and then we're going to use the kernel exit method, which is essentially going to do exactly the opposite. So we're going to LDP x0 and x1, stack pointer 16 times 0. And then the exact same for x2 and x3, 16 times 1. And we're going to do this for all of the registers again. And then at the end, we're going to add the stack pointer back to that S frame size and use ERET, which is going to return us from the exception. So this is, and you can see the first thing we do is we want to store the state, call our method, and then restore our state. That's the whole purpose of this kernel entry and kernel exit macros. So now let's go and create a irq.s file so we can actually use these exception vectors. And this is going to be in section D13.2.137. So I'll open that up in the reference manual. Here you see we have vbar el1. So this is just some information about the vector base address register here. So this is, again, useful information if you just want to read through it some to get some extra information and context here. So we're going to create our global method we're going to call, or function we're going to call IRQ init vectors. So we're going to use ADR vectors, storing the address of vectors into x0. That's this vector's value that we created here. So we'll store that value into x0, and we're going to use MSR to put that into vbar el1, and then return. So that's going to set up our vectors. So now let's look really quick in C5.2.2. In order to enable and disable our vectors, we want to use this register here, DAIF. It's the DAIF interrupt mask bits. So, and this DAIF have special meanings. D for debug. Yeah, we have A for the asynchronous, S error, interrupt mask, I for IRQ, and F for the fast IRQ. So and you'll see here in the register we have D, A, I, and F as individual bits. So those we would be able to set and reset to enable and disable these different functionalities. And so for enabling the vector, we're going to create enabling the interrupts, we're going to create a function here, IRQ enable. And all this is really going to do, we're going to use MSR on DAIF CLR, that's going to clear a bit number 2. So in bit number 2, we have F is 1 and I is 2. So clearing that bit is going to enable the IRQs. Now we'll simply just return from here, and we're going to do the same thing for IRQ disable. So we have IRQ disable. And the only difference here is we're using DAIF set. So to set that bit is going to disable it. So now let's create a little header file and put these functions in it. IRQ.h. Let's make sure we copy these names correctly. IRQ init vectors, and these are going to be called from our kernel code. So that's why we just need to put them in a little header here so they're easily accessible. So, and that's the initial part for setting up these IRQs. Now let's get into how to use these IRQs. We'll create an IRQ.h under peripherals here. And first let's take a look at we need to include these common things first, and then we'll take a look at the data sheets here. We'll start with the 2711 for the Raspberry Pi 4. We have this section of our IRQ pending registers, and this is at, you'll see B000 as the base. So we start with at 200, offset 200, we have IRQ 0 pending, IRQ 1 pending. At 204, at 208 we have IRQ pending 2. Then we have at 10 we have set enabled. And then we have the IRQ set enabled 1, IRQ 0 set enabled 2, and then the same thing for clear, enable 0, enable 1, and enable 2. And so the addresses here, you'll note, are similar to the Raspberry Pi 3, but the Raspberry Pi 3 has a little bit of a different order here. So if we scroll down here, we'll see at 200 we have the basic pending, which is IRQ pending 0, is the same thing, same address. So 200 is the pending 0, 204 is pending 1, 208 is pending 2. Then we have this FIQ control, which we didn't have in there. And now we have IRQ enable 1, 2, and then 0, and disable 1, 2, and 0. And if you remember on the other one, instead of 1, 2, and 0, we had 0, 1, and 2. This one is still 0, 1, and 2 on both, but the enables 0, 1, and 2, clear is 0, 1, and 2. Whereas on the Raspberry Pi it's 1, 2, and 0, and 1, 2, and 0. So we'll have to create different data structures for those two so that they don't conflict. So let's go here and just start by creating a structure here for ARM IRQ regs we'll say 2711, so this will be the one for the Raspberry Pi 4. Start with a reg 32, IRQ 0, pending 0. IRQ 0, pending 1. And then again, IRQ 0, pending 2. So then we have a reserved spot here that's not used. And then we're essentially going to have the same things here. So let's just copy and paste. This will make, let's see, we'll make this enable 0. Enable 1 and enable 2. And then another reserved variable. And likewise, we're going to have this same set here for disable. So that's going to be the basic structure of our IRQ registers, at least the ones that we're going to be currently using. So let's see, go back here to, let's create one here for ARM IRQ regs 2837. So this is the Raspberry Pi 3B. And this is essentially going to have all the same values. So let's just copy everything. We'll start with this one. After those three, it's going to have the fast IRQ control. And then essentially it's going to be all these same values here. It's just instead of 0 being first, it'll be third. So we'll put those right in order. This is just reserved. So now we have essentially the same registers that we're going to use. And now let's create a define, or actually we're going to create some type defs here. So if we're in Raspberry Pi version 3, we're going to type def struct ARM IRQ regs as ARM IRQ regs 2837 as ARM IRQ regs. And then we'll do the same thing for 4, except we're going to use 2711. So now down here we'll actually make a define to this pointer that we're going to use. ARM IRQ regs from pbase plus 0x0000 B200. So that's the variable that we're going to use to actually access these registers. So we'll go back into the data sheet here, and what we're going to do is jump down to the IRQ section, and this shows the different IRQs 0 to 15, 16 to 31 that we're going to be actually using. What I want to focus on here is this AUX interrupt. So this, if you remember, AUX is how we get access to the mini UART. So what I want to start doing is working on a way to capture interrupts from the UART. Instead of looping in our normal while loop, we're going to receive the updates as interrupts. So first let's create an enumeration here. We're going to use we'll call it VC IRQs, that's for video core. So we're going to have AUX IRQ equals 1 shifted over by 29, because that was the 29th bit in the IRQ list. So now let's go on into our, where are we going? Let's create a new file here called irq.c. So we're going to first include our utils, include some of our other headers here. We'll need printf, our entry.h. See, we'll need our peripherals IRQ, and peripherals AUX. we'll probably need the mini UART as well. So let's start off with adding the definitions, text definition map here for each of these invalid types. So these came straight from our entry.h header again, each of the 4 sections. So this is going to be just for some print friendly names for them. So we want to start by using our handle invalid entry. Let's see. Yeah, handle invalid entry. So we'll start writing the actual function. Remember, this is taking 3 parameters here, the type, the ESR, and the ELR, and it's passing to this function show invalid entry message. So we're going to create that function, show invalid entry message. It's going to take a U32 type, a U64 ESR, and another U64, the address, which is in that ELR register. So it's going to be a pretty simple printf error caught. We'll do the string, the type, and then the ESR value as hex, and the address as hex. So we'll pass in our function, our char array map here at index type, then type, then ESR, and then address. So this will print out this data whenever we hit an error. So now let's start with enabling the interrupt controller. So to enable the interrupt controller, we're going to have to do something different on each of the boards. So for the RPi version 4, we have a specific register we need to use. We can use regs IRQ 0, enable 0. That's because if you go through the data sheets, the 0 through 32 registers are on that enable 0. And we're going to set it to AUX IRQ because that's the only one that we're using currently. And so for the Raspberry Pi 3, it's actually the enable 1 register. A little bit confusing, but the 2 boards they're different. They're different interrupt controllers. So now we'll just handle our handle IRQ method. So on this one, we kind of have to do the same sort of thing here. Each of these has a different register that it picks the actual IRQ from. So for the Raspberry Pi 4, it's IRQ pending 0. And we need to create a variable here. So U32 IRQ equals that IRQ pending 0. And then for the 3, it's on the pending 1. So now what do we do with this IRQ? So we know that we got one. Well, it could be multiple. To start with, we only have one, but for right now, we're going to say while it's an actual valid value, we're going to see if the AUX bit is set, or hold on, that's yeah, IRQ and equals, and so that should be AUX IRQ and equals the inverse of AUX IRQ. That's so we can just loop and remove the bit that we've already handled. Of course, right now we only have one, so it doesn't matter so much. But let's jump back here and let's look up the mini UART registers again. So we have this MUIIR register. So this is the one we're gonna be concerned with here. You'll see it has on bits 2 and 1, we have a receiver holds a valid byte. So we need to check, does the receiver hold a valid byte? So that would be the value 1, 0, but at offset 2, 1. So that's going to be 4. If you imagine you put a 0 after that, would be 4 in binary. So if that 4-bit is set on the MUIIR, while and4 is equal to 4, then we know that there is data to be read. So we'll just printf UART receive, and then we'll just do a UART send, UART receive. And then we'll print a new line. So that's what's going to happen whenever we get the IAR register showing that there's data to be read. So now let's go back up here to the IAR register. This is how we're going to enable the AUX MU interrupts. So if we look here, we have enable receive interrupt is bit 1. So if this bit is set, whenever the receive FIFO holds at least 1 byte. So that's the value we want to actually set in our mini UART when we're starting up regs AUX MU IAR equals 2. So now let's jump back into our kernel, and we're going to copy this function first, enable interrupt controller, make sure that's in our header. We'll jump back into our kernel here, and we're going to include this irq.h here. And then after our initializing a printf and UART, we're going to call this function enable interrupt controller. Then we have the other functions such as, let's see, IRQ init vectors. Let's see, that one we actually want to call first, so init vectors. Then we'll call IRQ enable to enable IRQs. Now we're going to take this part out here where we normally send and receive just in a loop. So we'll just loop continuously doing nothing. And let's go ahead and build, let's create a new terminal here, make clean, make for RPi version 3. Well, we have an error, let's see. Okay, yeah, that's just because we forgot it's IRQ 0 pending 0 and IRQ 0 pending 1. Make again. Alright, so now let's put this in our Raspberry Pi 3. Jump back over to our console here. Now it's booting up. And okay, so it started up. So now I'm typing here. These are just the different letters that I'm typing. This is a test. You can see that all works as expected. It looks pretty good for Raspberry Pi 3. So let's jump over here and we'll do Raspberry Pi 4. So we'll do make clean, make RPi version of Raspberry Pi 4. Alright, so we'll take this SD card and put it in the Raspberry Pi 4 here and jump back over to the console. Just gotta move these cables here. Alright, so here we go to the console and you see it's booting up. Here we go, accept to level 1, and as I'm typing, exact same results. So it looks good. So I think we're at a good stopping point. This has been a bit longer than the other videos, but I wanted to make sure you understood how to initially set up the interrupt controller and the section vectors all together and actually use the IRQ for the mini UART. In the next video, I'll show you how to use the IRQs for the system timers, and with that we can create an accurate delay function using the system timer interrupts. Once again, if you enjoyed this video and learned something from it, please like and subscribe and comment with any questions you may have. Thanks for watching.